Right, we've got a worked example here for a ladder problem. These are the sort of harder end of the moments problems that we get in the forces section. And this one is a particularly tricky one. I think this is probably as hard as you're going to get in A-level maths. So if you can do this one, you can probably do them all. Let's have a look. A ramp AB of length 8 meters and mass 20 kilograms rests in equilibrium with the end A on rough horizontal ground. The ramp rests on a smooth, solid cylindrical drum partly under the ground. Okay, so it's kind of sort of buried under the ground, and that's the top half of the drum there, the ramp resting against it. The point of contact between the ramp and the drum is C. AC is 5, and then we've got the rest 3 meters sticking out the top there. The ramp is resting in a vertical plane, which is perpendicular to the axis of the drum. That just means that the ramp isn't pointing away or towards us or away. Um, it's all in the plane of the paper. Um, and tan theta, is the angle here that the ramp makes to the ground, is 724. So and from that we can calculate this is 724, 724.25 is a Pythagorean triple. So basically that gives us the other trig functions quite easily. The ramp is modeled as a uniform rod, which means that the mass is acting from the center. Um, First of all, explain why the reaction from the drum on the ramp at point C acts in a direction which is perpendicular to the ramp. Okay, so we've got our forces diagram here. So I've populated this. What have we got? Well, there's sort of three main things really. There's first of all the reaction here at C, and just to answer question A, I mean that's always perpendicular to the surface. So and so this is a tangent here. So this is normal to the tangent at that point. Secondly, we have got the weight of the rod there bearing down from its midpoint here. Um, uh, yeah, we've got the measurements here, 4, 1, and 3. And then we've got the normal reaction acting at A. But not only normal reaction, because this is rough ground, so we've also got some friction acting here as well. All right, so those are the forces that we've got to think about. So so part B then, so the tricky part, find the magnitude of the resultant force acting on the ramp at A. Right, well, in order to do that, and so we've got this force and we've got this force. We need to find both of these forces, and then we're essentially looking at triangle forces to give us the resultant force. Right, kind of our first thing here is that I think we should be able to observe that if we take the moments about A, we kind of going to get rid of some of this complexity around here in the friction in the first case, and that's sort of generally true of these moments problems. If we take moments about a point where there are forces that um, um, we don't need for this particular stage, and then yeah, it will eliminate those forces. So therefore, if we're taking moments about there, what we're interested in are, so obviously we've got to be kind of perpendicular to the line of which we're taking the moments. So the clockwise force is this resolved part of the weight, so that's 20g cos theta, this angle here being theta. So that's 20g cos theta times this distance here from A to that point there, which is 4. And then anti-clockwise, we've got the reaction force R, which it's called R. Okay. Right, so that works out quite nicely. So those two moments are equal. So r times 5, that one there, times the distance, is equal to this, whoops, this force here times that distance, which is 4. So r is going to be equal to that, which works out 150.528 newtons. Okay, we could have probably left it like that because that's not the final answer, but it kind of it sort of suits to actually turn this into a number. Right, okay, so go down. This is such a kind of big problem and solution. What I've done is I've replicated the diagram over here. All right, so so that's good. So I mean, we've found R. The reason we're finding R really is in order to be able to find this normal reaction here. Because now, if we look in the linear sense at this, what have we got? We've got this, we've got this, and we've got this. So looking at linear forces is always a big part of these moments problems. Ladder problems are particularly difficult, obviously, because we've got to resolve forces in different directions as well. So that's where a lot of the complication comes in. But in this case, so we're just looking at these three. So we can just pick these three forces out here. So, and of course, this reaction force at A is N. So, so N plus these are the vertical going up forces. N plus R cos theta. Well, this is R here. We kind of established that R cos theta is going to equal 20G. That force down there. Right, so if we just work that one through, I mean, we know all these things here, so N just works out. We've got cos squared there, so it's kind of unusual for these kind of things. But so that works out basically is that N is 51.493 newtons. Right, okay. Now the other thing is that we want F, don't we? Now, I think we'll look at this problem. I was tempted to kind of try and identify the horizontal forces, but in actual fact, we want moments about C in this situation. If we take the moments about C, then what have we got? Again, we've got to be perpendicular to the sort of the line that we're using from C along the ramp. So now this N resolved perpendicularly is going to be N cos theta, and that's acting at 5. Yeah, from the point C, and then the anti-clockwise ones are first of all this resolve part of the weight 20G cos theta, which is acting at 1. 20G cos theta times 1. And then we've got this friction. So if we resolve this friction in the direction perpendicular to the ramp, then that's going to be F sine theta and times the distance from C to A, which is 5. Right, so if we rearrange all that, to be explicit in F, it looks like that. Well, we know all these things, so we can stick that into our calculator, and it's going to give us that F has got a value of 42.147. Right, so the resultant force, now if we're just looking at our triangular forces, it's just a Pythagoras type calculation. So n squared plus f squared. And when we plug those in, then basically what we get is this result that it is 66.543 newtons. And I should put the accuracy on there, which is 3 significant figures. All right, so that is the magnitude of the resultant force acting on the ramp at A. So we've used rotational forces to find R. We've used linear forces to find N, and then we've used rotational again to find F. So yeah, sort of kind of quite involved really. All right, there's a last part of this. The ramp is still in equilibrium in the position shown in the diagram, but the ramp is not now modeled as being uniform, given that the center of mass is assumed to be closer to A than B. All right, so this thing moves down here. How would this affect the magnitude of the normal reaction between the ramp and the drum at C? I think it's fairly intuitive. It's going to reduce the normal reaction. As because this here has then got, we're taking moments about there, the clockwise moment is going to be reduced, isn't it? You know, if it's that force there, for instance, then the clockwise moment is reduced, and therefore, because it's in equilibrium, the anti-clockwise moment will reduce as a result, and the distance stays the same. So obviously, the reaction force has got to reduce as a result. Okay, so that's basically it. So I hope that helps, and thanks for listening.